Welcome back. Today we're going to look at some things about the quantum model of the atom. So we've talked about primitive models. We talked about the original atomic model that simply says that if you devise something, eventually you're going to get to an indivisible size, which we would call then the atom or indivisible. And then the discovery that there were electrons in matter made by J.J. Thomson. And so then the development of the plum pudding model, saying that we have a nebulous positive charge with small electrons or points of negative charge. Then to the Rutherford model, where they discovered that no, it's mostly empty space, but you have a really massive charge, positive charge center. And then finally, we ended with the Bohr model. The Bohr model saying that there are quantized energy levels and quantized angular momentum, and he had the same quantization number, n, a quantum number, for all of them. So n, that quantum number, told you what the energy of the electron orbiting the nucleus was. It told you what the radius of the electron orbiting the nucleus was. It told you what the velocity of the electron orbiting the nucleus was. It told you that, everything. Well, now we get to the quantum model. So first, just to review from last class period, the successes of the Bohr model were, number one, it agreed that we had mostly empty space. That was the discovery of Rutherford. And it predicted energy levels that matched those observed in the hydrogen emission spectrum. And it gave a reason, even if the reason is simply it has only certain energy levels, so it can't continuously change, why they don't radiate and fall to lower energy levels. But big failures. It couldn't explain why some emission lines are stronger than others, and some that should exist don't exist. And it couldn't explain why you have this splitting of lines. So we're going to get into this today, talking about the quantum model to help explain those. So the quantum model is treating the electron as a wave and finding its wave function and finding all different properties. And if you take quantum mechanics, which I guess won't be from me next year, you will learn how to do the calculation and how we come up with these quantum numbers. For the purposes of general physics, we don't go through how the numbers come up, but we'll go through what they are. But first, we start with really what drove people to quantum physics for studying, well, this is what drove them to quantum physics. It was studying the atom and the frustration that they simply could not identify where the electron was or what path the electron was taking. Now, Bohr had said it does a circle, but they couldn't come up with any answers for where it is and couldn't measure, and it was crazy. And so they kind of gave up and went a different direction. That's what Heisenberg did. Just went a different direction. He said, well, what can we quantify? And so he put down the properties that they could determine about the atom, things like its magnetic moment and its energy and whatnot, and went about it and developed quantum mechanics. So when we treat the electron as a wave, you have a localization problem. For a particle, where's the particle? It's right here. I can touch it. I can point to it. It's right here. But for a wave has a spread out position. And so the exact position of the wave isn't really defined. So when we're talking about the quantum model, we have, well, the wave has a higher amplitude here and a smaller amplitude there, so it's more probable that I'll find it here where we have a higher amplitude, less probable that I'll find it here with the lower amplitude. So quantum mechanics is at its root probabilistic. It's based on probabilities. You might have heard the famous quote by Einstein saying, "I don't believe that God plays dice with nature." He did not find it comfortable or easy to accept that we're dealing with probabilities, that what's going to happen is based on statistics and not based on absolutes. Einstein felt that if you had enough information, you can know exactly what's going to happen. But quantum mechanics says that's not the way nature works. So when you see pictures, and I show you this picture, I know last class period, we see a picture like this of an atom. This is what we would call an S orbital, which you probably all recognize. And it's telling us that we have a certain probability shape. The probability of finding the electron within this is very high. The probability of finding it outside is very low. Now, in terms of quantum numbers, the principal quantum number n in the Bohr model, that was the only quantum number that primarily was there to tell us the angular momentum, but as a result of physics, told us everything. In the quantum model, n is called the principal quantum number. There's the word principal quantum number. And it tells us primarily what the energy is. And the equation for the energy here fundamentally is the same as we had from the Bohr model. So it seems like we haven't made a change. In fact, when I was in high school, my teacher was teaching this same thing to me. I didn't distinguish that there was a difference between the Bohr model and the quantum model because, I mean, we have the same energy equation with the same n. And if it was that simple, well, life would be, well, simpler. But that's not the case at all. In fact, we'll talk about how the energy is affected by other things later in this lecture. But then we have the next quantum number. Since, remember, Bohr said n was going to tell us the angular momentum, now we have a different quantum number. So we have lowercase l that is called the orbital angular momentum quantum number. And this lowercase l can have values of 0, 1, 2, etc., up to n minus 1. So if n is equal to 1, which is the smallest n value you can have, n has to be an integer above 0. So if n is 1, L has to be 0. If n is 2, L could be 0 or 1, and so on. And this tells us the angular momentum, but not in nearly as straightforward a fashion as Bohr had tried. If, let's say, if L, the quantum number, is equal to 3, then the angular momentum is equal to the square root of 3 times 3 plus 1, or 4, times h bar. So, of course, 3 times 4 is 12, and so this is equal to square root of 12 h bar. So the angular momentum, notice this square root of 12 is bigger than 3 and less than 4. So it's bigger than L, but less than L plus 1 for the coefficient of h bar. And h bar, in quantum mechanics, we say that's the unit of the angular momentum. Remember, h bar, the reduced Planck's constant, is Planck's constant divided by 2 pi. But then we have the orientation of angular momentum. Angular momentum, you know, we know about angular momentum. If you rotate, angular momentum is the propensity to stay in that same rotation. But you could be rotating about different axes. And so we have L sub z, which is an arbitrarily defined direction. The z direction is, if we put in a magnetic field, the direction of the magnetic field is what we call the z direction. And so L sub z is the angular momentum component that is in that arbitrarily defined direction. And it turns out that that is integer multiples of h bar. And so we have m sub L, which is the orbital magnetic quantum number. And you might wonder, magnetic, what does that have to do with magnetism? Well, at least m goes with magnetic, right? But here's what it has to do with magnetism. You have a charged particle with angular momentum, and that gives it a magnetic moment. In fact, magnetic moment is really what our observable is. We observe the magnetic moment. We observe how it responds to magnets. And so m sub L is telling us about how it's going to respond if you put it in a magnetic field. Now, the angular momentum could be in any direction. So let's draw a circle here. And we have, here's our atom, and the angular momentum could be, for instance, pointing this way or pointing this way, or, you know, whatever. But then we define the z-axis. So here's our z-axis. And now we have the angular momentum has a magnitude. I'm going to erase those because one thing I didn't do is draw them with the right length. It has a magnitude that is on that purple circle. But the actual angular momentum could be 0 in the z direction. So that's angular momentum if m sub L equals 0. Or it could be 1. or it could be minus 1. These are times h bar. But if we were to go to, in this case, I'm using L equals 1. So if L is equal to 1, then that means the maximum capital L is equal to square root of 1 times 2, which is 2 h bar, or 1.41 h bar. So the amount of angular momentum when L is equal to 1 that is in the z direction cannot exceed 1.41 h bar. So this here had h bar. This here had minus h bar. If we were to go to m sub L equals 2 or minus 2, we would have 2 h bar or minus 2 h bar in the z direction, and that's not possible. So the only possible values for m sub L are going to be the values where L sub z is, yes, that was right, is between negative L and positive L, or h bar square root of L times L plus 1 minus that is less than LZ. Well, for LZ, we'll put m sub L h bar is less than h bar square root of L times L plus 1. So what that gives us is the result that my m sub L could be anywhere from minus L up to L. So that's what this is saying, minus L to plus L in steps of 1. So it's any integer going from minus L to plus L. I know that's a long way to explain something you probably already knew, but maybe didn't understand why. So we have 2 quantum numbers already, or 3 quantum numbers. We had n was the principal quantum number. L was the orbital angular momentum. M sub L was the orbital magnetic. Oftentimes we'll just call it the magnetic and just call that the orbital. And now we have one more. And on this screen, you see the number capital S. Capital S is the total spin angular momentum. Now, spin is a misnomer. When scientists were first studying the atom and the electron, they thought, well, the electron has a charge, it has a magnetic moment, so it must be spinning so that it makes a magnetic moment, charge going around the circle. And so they called it the spin. But in studying electrons, we don't know the size of an electron, but we know it's smaller than X value. And based on its size, it's not possible for the electron to spin fast enough to create its magnetic moment. So we know absolutely that the spin does not represent spin of an electron. It's something else. And we believe it's simply an intrinsic magnetic moment for the electron, that it's basically a little bar magnet. Capital S, the spin, is always h bar times square root of 3 over 4. Lowercase s is going to be the orientation of the spin. And so I'm going to put m sub s is the spin orientation. So notice it's an M. It's magnetic. It's something that we measure with magnetism. And so the magnetic moment is going to be either S sub Z is equal to ms h bar, and m sub s has only values of minus 1/2 or 1/2. Things that have 1/2 integer values for their spin we call fermions. So electrons are fermions. And when we get to the Pauli exclusion principle, that is something that applies to all fermions. So m sub L went from minus L ... to plus L, any integer in that range. L went from 0, dot, 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 n minus 1, and n was 1, any positive integer. So those are the 4 quantum numbers that we use to describe an atom. So here is what I just wrote about the spin magnetic quantum number, m sub s. And so the Pauli exclusion principle is a result of the calculations for what happens if you have 1/2 integer spins. We have actually Bose-Einstein statistics for integer spin particles. Like a photon has integer spin. And then we have, I'm going to change color just to be pretty, Fermi Dirac statistics for half integer spin particles. And that would be things like electrons, also protons and neutrons. So these things in this category we call fermions. These things in this we call bosons. So boson just means it is obeying the Bose-Einstein statistics. Fermion means it's obeying the Fermi-Dirac statistics. And so just examples of fermions, just to make sure we've got that in our heads. Protons, neutrons, and electrons. And when you look at the Fermi-Dirac calculations, they show that you can have no wave function if you have 2 indistinguishable particles that have the same set of quantum numbers. So for these particles, you have what we call the Pauli exclusion principle. That says no 2 indistinguishable fermions can have the same quantum numbers, same set of quantum numbers. Now let's be clear. What does it mean for them to be indistinguishable? I mean, you can't tell one proton from another, right? But if I have one proton in this atom and one proton in another atom, those are distinguishable because they belong to different atoms. Likewise, if I have 2 electrons orbiting one hydrogen atom, well, that wouldn't work, right? 2 electrons orbiting one helium atom, I can't distinguish one electron from another. So those are indistinguishable. They must obey the Pauli exclusion principle. But if I have 2 hydrogen atoms, each one having an electron orbiting it, I can tell those electrons apart because one is with one proton and one is with the other proton. So that's when we talk about the Pauli exclusion principle. In practice, it's only going to apply to electrons in the same atom. Example of bosons, there aren't nearly as many examples, but the primary one we talked about is the photon. We have all the gauge bosons, the particles that mediate forces are bosons, but we'll just leave it at that. So just a review question, make sure you're with me. How many quantum numbers are required to specify the state of a hydrogen atom? So I say the state of a hydrogen atom here because the hydrogen atom, it has 1 electron. So we're describing the state of that 1 electron. It gets more complicated if we have a helium atom with its 2 electrons. So that's why we have the hydrogen atom. And if you want to be really honest, we're really not talking about just the electron. We're talking about the atom. We're talking about the interaction between the nucleus, in this case a proton, and the electron. And so we've just listed them. We had the principal quantum number, n. We had the orbital angular magnetic quantum number, orbital angular momentum, I hope I said that, L. We had the orbital magnetic quantum number, M sub L, and we had the spin magnetic number, M sub S. 4. So you notice I put only one word from the long descriptions. Spin was spin magnetic. Magnetic was orbital magnetic. Orbital was orbital angular momentum. So the words can be a little fuzzy, and I try to be clear, but yet here I want to write it quickly, so I wrote the keywords. So here is a fundamental listing of those, and here's the words I wrote. And you can see the full. And of course, the restrictions on what the values can be. You should know these. You should know what the restrictions are. So if you put electrons into an atom, the electrons are going to fill from lowest energy up. And so we have a lot of complications in filling. But the first thing I want to focus on is how you order the electrons. Let me throw an extra page in here just so I have room to write. Insert one page. So let's imagine that I have an atom that has one electron. Well, I have n equals 1 is the lowest energy. You might be, how does he know that? Because we have the equation that energy is equal to 1 over n squared. Well, let me put z squared over n squared so I cover anything, times that minus 13.6 electron volts. So n equals 1 is minus 13.6. N equals 2 is 1/4 of that because it's 1 divided by 2 squared. N equals 3 is 1/9 and so on. So the lowest energy is n equals 1, which we call the ground state. And so n equals 1, the first electron is going to go there. But there's other quantum numbers. If n equals 1, L has to be between 0 and n minus 1. Well, that means between 0 and 0, so L must be 0. Then M sub L must be between minus L and plus L, which means that's equal to 0. Those all, if n equals 1, the two in red have to be. And then we have M sub S, and that could be either 1/2 or minus 1/2. So the first electron in is going to have these three numbers, and then it has one of those two. Now, what if I change it to having 2 electrons? If I have 2 electrons, then the first electron, let's say, goes to this. Then the second electron can have the same energy, 0, 0, and minus 1/2, because those are two different numbers. So that means I can put 2 electrons in n equals 1. So what happens if I have a third electron? Well, if I have a third electron, the first two are going to be n equals 1, L equals 0, M sub L equals 0, M sub S equals 1/2, and then the next one will be 1, 0, 0, minus 1/2, the same as we saw for the 2 electrons, but now we have a third electron. So the third electron is going to have to go to n equals 2. And if n equals 2, L could be minus 0 or 1, and M sub L, if it's 0, M sub L would just have to be 0. If it's 1, it could be minus 1, 0, or 1. And then for all of these, you have 1/2 and minus 1/2. So if we look at this, with n equals 2, if L is equal to 0, we once again have 2 electrons that can go in. There's 0 and 1/2 minus 1/2. If L equals 1, we have 3 possible values for M sub L, and each of those having 2. So we have a total of 2 electrons in n equals 1, L equals 0. 2 electrons can fit in n equals 2, L equals 0, but 6 electrons in n equals 2, L equals 1, because we have 3 possibilities here multiplied by 2 possibilities here. 3 times 2 gave me 6. So the electrons will fill in from lowest energy up. Now, to make life easy, spectroscopists have come up with abbreviations for the values for L. N we call the shell. So N is the shell. So N equals 1, that's the first shell, called the K shell. N equals 2, the second shell, called the L shell. So shell N, the K shell is N equals 1. The L shell is N equals 2. M shell is N equals 3, and so on. So those are the shells. Now for the subshells, or orbitals, those go with L. And so for the subshell, you have L could be 0, and they call that an S for sharp. And then you can have L equals 1, and they call that P for principal. L could be equal to 2, and they call that D for diffuse. L could equal 3, and they call it F. I believe that's for fine. And then after that, they follow alphabetical order, except for we skip 1. I can't remember if it's I or J, but they skip 1 letter in the alphabet, but it follows alphabetically after that. And in terms of the number of electrons that you can fit in these subshells, you can fit 2 in an S, because that was 2 times 1. And actually, if you think about it, because L goes between, or M sub L goes between minus L and plus L, then you have 2L plus 1 values for M sub L that are available. And so the number of electrons in a subshell is equal to 2L plus 1 for the number of M sub L's multiplied by 2 for the number of M sub S's. So if L is equal to 1, you have 2 plus 1 is 3 times 2, 6. If L is equal to 2, then you have 2 times 2 is 4, plus 1 is 5, times 2 is 10. And if L is equal to 3, 6 plus 1 is 7, times 2 is 14. If L is 4, then you have 9 times 2 is 18, and so on. And as you can see, each one's just going up by 4. So electron filling, it's going to fill from lowest energy up. Now, it's not as simple as I'm making it look right now. We'll get more on that in just a minute. But when we talk about the filling of the shells and subshells, we have the shell here is indicated with a number, N. We could have said K for N equals 1. In this case, if N is equal to 2, what is that? Yes, that's an L for N equals 2. But we typically don't show the shells here. We just put the number. So 2P3, P means L is equal to 1. S would have been L equals 0. And then the 3 is how many electrons we put in that N equals 2, L equals 1 subshell. Look, we already did this, right? Now, Hund's rule. You probably have learned Hund's rule. In general chemistry, you learned that when you put the electrons in, you always put the up arrows first, and then you put the down arrows. And did you ever wonder why? I mean, well, you may have, you may not have. Here's the reason. You can only put 2 electrons in each, that's each, not whatever I wrote, in each M sub L. And one is going to be spin up, or m sub s equals 1/2, and one spin down, or m sub s equals minus 1/2. But in terms of energy, if you have the magnetic moments aligned together, it's lower energy. And the electrons always go in lowest energy state possible. And so having the three aligned together is lower energy. Having these paired up is a higher energy. So it's not going to pair up unless it has to. So that's why this one doesn't naturally, it's not the natural alignment. Now, I told you things are going to be more complicated. Well, it turns out that the energy, this is what you would get from the Bohr model. But with the quantum model, you have energy associated with those magnetic moments, as well as a few other things. And so the energy levels actually shift. All of this here could not be explained by the Bohr model. And you're like, well, this is just, it's just a graph that somebody made. Why does the Bohr model not explain it? Well, we do have a measurable. The measurable is looking at the absorption and emission spectral lines. The absorption and emission spectral lines are the energies, the energy differences between allowed states. So for instance, this would be one energy. This would be another possible energy. And this would be another one, and so on. Yeah, I'm thinking about this carefully because I don't want to write not allowed transitions. But we have all of these different transitions which give us different energies in the spectra, and not all of these could be explained by the Bohr model. But with the quantum model, we have these explanations. But the thing to note here is you start to have some overlap. N equals 3, if you're in the n equals 3, m sub l is equal to 2, that's going to be a higher energy, L equals 2. That's going to be a higher energy than n equals 4, L equals 0. And so it doesn't just go to the lowest NL combination possible. It does something a little more complicated. So this here is the memory device that my teacher in high school taught us. And when he taught us, I thought it was the most amazing thing. Now I've come to understand, okay, so it's not based on any solid scientific reasoning. It just happens to work correctly for the range into which we use it. So when you put electrons in, the first 2 electrons go in the 1s. The next 2 electrons go in the 2s. Well, let me talk about how we make this. You make this by putting the 1s's starting at 1 at the bottom and going all the way up. And then the p's, so 1s, 2s, 3s, 4s, etc., all the s's. And then the p's, you don't have a 1p. Starts with 2, so in the row for 2, you put your 2p and go on up. D's, you don't have a 1 or a 2p, you only have a 3p, D and higher. So you start there and you draw them up. And then you draw these diagonals. And the diagonals actually work out to give us the filling order. So the first 2 electrons go in the 1s. When you finish this one, you just go over to the next available row and start up. So after 1s, it'll fill 2s. Go over the next available, actually I said row, column. The bottom of the next column is 2p. So 2p, then 2s. Go down to the bottom of the next one. There are 3p is at the bottom of it. 4s, bottom of the next one, 3d, 4p, 5s, and so on. So you can actually figure out which electrons are filled, except for some exceptions that occur, by following this little diagram. So it's really useful just for figuring out, okay, which electrons fill. And this is what dictates the periodic table. Group 1 here are S1. Group 2 are S2. Group 13 are P1. So you have S2P1. Okay, I'm not going to worry about that. I'm just looking at the last one filled. Group 14 is P2, etc. Get out here to the halogens, that's P5, and then the noble gases, P6. Well, what about these down here, the transition metals? Well, this should be D1, D2, etc. All makes good sense, right? Following these rules, first electron, S1. Second electron, S2. This one here was an outlier. That's an S2. It's the only S2 that's in that final column. In fact, you might see some periodic tables that show helium right here because it is S2. So 1S, 1S1, 1S2, and then we go to 2S1, 2S2. The next one, 2P1, so on. And so we get to the end of 2Ps. There's the end of the second row. After each, before each S, you end a row. So before 2S, we end. Before 3S, we end. Before 4S, we end. Before 5S, we end. So we come across here. It all makes perfect sense. We get down here, and we have our first disruption. Because we have 3S1, 3S2, we don't put a 3D1. We go straight to 3P1, 3P2, and we fill those. Then we have 4S1, 4S2. Then we do our 3D1. And we go on from there. So these are shifted down a row because we are 2P, 2S, 3P, 4S came before 3D. But there's more interesting things to note here. Okay, so this is indeed 3D1, 4S2. They put the 3 first because, of course, that's a lower shell. 3D2, 4S2, okay, nothing special there. 3D3, exactly what we expected. 3D5, 4S1, what happened there? Well, it actually goes back to the same idea as Hundt's rule. So remember, with Hundt's rule, we're going to have lower energy if they're aligned. And so for that one, we had a total of, okay, so it was 3D5, 4S1 was what it had. So that's 6 electrons that we're putting in. And so if you have, here's the 4S. And these are the 3D. And so for lowest energy, when they're aligned the same, it's the lowest energy. And so it moved the one that had been paired here out so they would all 6 be aligned together because it's lower energy. So that's why we have, oh boy. Sorry about that. I have my phone on silent, but it rings through my computer. So chromium has that unique structure because it has them all in the same direction, so lowest energy. Then manganese is normal, and you keep going until you get out here to zinc. And again, you see with copper and zinc, copper, it went to 4S1 3D10. So it didn't put 9 in the Ds, it put the 1 lone in the S. And then finally we have zinc is the normal. So there's some unique things that occur because everything is happening to give us the lowest possible energy state. These periods are telling us the values for N, at least for the first and the last row. So N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, 6, 7. We have a shift here on the P's. The P's come in 1 row late or 1 period late. And the D's come in, right, in reality, we should have an all S's here, S and P here, SP and D here, but the D is delayed. We should have SPDF in the fourth period, but the Fs don't show up until here. So the Fs are delayed by 2 periods before they show up. And typically, we show the Fs, filling of the F orbitals, down underneath just so that we can fit the periodic table on a page. So these lanthanide and actinide series should be going in there, and that's filling the Fs. Now, selection rules. Remember, we did have spectroscopy was the topic of the day. When you have an electron that falls from a higher energy state to a lower energy state. So for instance, I'm going to go from here to here. The energy difference between these two states comes off as a photon. But that photon doesn't just carry energy. The photon also carries momentum. We saw from relativity, the momentum of the photon is equal to h over the wavelength, or if you prefer EC, E over C. So it carries momentum. It also, believe it or not, carries angular momentum. It has angular momentum, that is, it has L equals 1. And so when an electron falls from the 3p, for instance, to the 1s, it has to have conservation of momentum and energy and angular momentum. So since the angular momentum dropped from L equals 1 to L equals 0 when I went from 3p to 3s, the angular momentum of the photon had to be 1. And in fact, since the angular momentum of the photon is always 1, you always have to have the change in L is 1 for an allowed transition. So I can go from 3p to 1s, that's a change in n of 2. Delta n can be anything. But we had to have delta L equals plus or minus 1. So going from a p to an s, that's going from L equals 1 to L equals 0. That works. You cannot have going from 3p to 2p. That doesn't occur because delta L equals 0. You could go from a 3s to a 2p. You could do this. Let me change colors. I'll put in blue allowed transitions. 3s to 2p works because your L went up by 1. You can't go from a 3s to 2s or to a 3 to a 1s because you have to have a delta L of 1. So there's only certain transitions that it can occur. 2p to 1s, sure, that's a change of 1. You cannot do 2s to 1s because that would be a delta L of 0. You can't go from a 3D to a 2s because that would be a delta L of 2. So this is a result of conservation of angular momentum that says that those cannot occur. Now there's another rule, and this is, I'm being specific to the hydrogen atom. It gets more complicated when you have more than one electron because you can have coupling between the electrons, so a disallowed transition can occur because it couples with another electron. The final rule is because the momentum has L equals 1, or the photon has L equals 1, then M sub L could be equal to minus 1, 0, or 1. And so you also have to have a change in M sub L that's either minus 1, 0, or 1 when you have a transition. So the spectra is restricted. It's not just any change between two lines because it has to follow M sub L. It has to follow these rules for it to be an allowed transition. So we call those the selection rules, and this is another success of the quantum model. The quantum model gives us a reason why some of these transitions that should occur don't occur because of these selection rules. Now, the last thing for today is going to be looking at what these quantum numbers mean with regard to orbitals. So you probably have learned in chemistry class about an s orbital and a p orbital and so on. You know what they look like. Well, I'm going to go to this place that we call orbitron, and yeah, you can see it's opening up. And we're going to look at some really cool things. Oh, I forgot. I don't have all of the software to make all of this work. But it shows us orbitals. So a 1s orbital. Please go to the 1s orbital. So this is what we look at for the picture of the 1s orbital. And that's pretty boring. It's just a circle. The wave function is showing us the calculation of how we got there. And this is giving us the probability of, well, it's not the probability of the radius, but it's related to the probability of the radius. And if you look at this, probability of a zero radius is the highest. But we really need to take into account the volume as well. And so if you take into account the volume, this is the true probability of radius for an electron in the 1s orbital. That is n equals 1, l equals 0, m sub l equals 0. And so this here is telling us the probability of having a different radius, different radii. And so this here, it had on here before the writing tools, and now I got rid of them. Extra good. Well, right here, you can probably see it's lighter. That's the highest probability. And thus, it turns out exactly the same as the Bohr radius. So another success, the Bohr model matches the quantum model in predicting the Bohr radius. Now that's a 1s. If you look at a 2s, the 2s has, I swear it's coming, there it is. The 2s, the picture, that looks the same, but notice we have an inner and an outer part. So if I go to the radial distribution, I'm only going to look at the radial distribution and the first picture from now on. The radial distribution, we now see that we have two places of peak likelihood. And so you have an inner region where you're likely to find an outer region. And this is if you make a measurement and you find what the distance between the electron and the nucleus is going to be. That's what you're going to find for the most probable. So that's a 2s. What about a 2p? Everybody probably knows a 2p looks like a dumbbell, right? Well, let's look at the 2p just to see what this shows. And sorry, the web page is just slow. So here we have dumbbells, but we have the dumbbells in three different orientations. Three different orientations because you have different directions for the angular momentum, that L sub z. And so let's go to the radial distribution and look at what the radius function looks like. And you might be surprised to see this radius function looks exactly as it did for the 1s. And in fact, if we go to the 3D, it's going to look that way too. Now I'm going to go straight to the 3p before the 3D. 3p, it's another p orbital, so dumbbell shaped, right? Well, not exactly. See, we've got some curiosities there, some things that aren't exactly dumbbell shaped. And if we look at the radial distribution for the 3p, we'll see it looks like the 2s radial distribution. And then the 3D, now what does a d orbital look like? Probably most of you are starting to scratch your head when you get to what does the 3D orbital look like. We have these shapes here all look the same, just different orientations, but that one there, which is the m sub l equals 0, looks completely different. What about well, I like to look at things like the 4p, 4d. Let's look at the 4d. Down to me. So the 4D, you see it got more complicated, but it was the same basic thing. The 4F, F orbitals are unique. They're cool. There's my 4f orbitals. Very cool, right? Very cool. And you can keep going through here. It has other things to help you. Things like, have you ever wondered what an sp3 hybridized orbital looks like? Well, here you have it. The sp3, these are all quantum physics calculations. There's what the sp3 looks like, or the sp2. I won't do sp, it's too boring. There's the sp2, 3 different sp2s. Or you might wonder, what does an antibonding orbital look like? So here's H2 with antibonding. The electron shells repel each other as they get closer. Whereas with bonding, the electrons are going to be shared. And so that's bonding. Or you can look at things like a pi, let's just go to a pi bonding. Okay, so that's a really cool website. One that I recommend you play around with. It's really fun. Last couple things that could not be explained by the Bohr model that we can explain with the quantum model. The Zeeman effect. The Zeeman effect is splitting of spectral lines in a magnetic field. So this is just one transition here. And if there's no external magnetic field, you just see a single line. But if you put a magnetic field, it splits out. So this time it split out into 3. Here it split out into 5. And if you make the magnetic field stronger, the split gets stronger. And that's something that could not be explained by the Bohr model. But now that we have this whole understanding about the magnetic moments, and we can talk about the energy levels due to magnetic fields, we can explain those with the Zeeman effect. We use that, for instance, to calculate the strength of the magnetic field on the sun. We look at spectral lines of the sun, and we look at the splitting, and we can determine by looking at how much the lines have split, how much the wavelength is split, what the strength of the magnetic field is. Last slide before a question is fine structure. Fine structure, one of the failures of the Bohr model. Fine structure, you look at these lines, it looks like one, but if you really zoom in, it's actually split. And we now understand that because the electron could have its magnetic moment aligned with or aligned against the magnetic moment of its orbit. If it's aligned with, it's going to be a lower energy. If it's aligned against, it's going to be a higher energy. So you have an energy difference giving us that split. Okay, final question. Which statement is the Pauli exclusion principle? This was one of Bohr's rules. This one here, Pauli exclusion principle. All right, have a great day. Bye.